Okay, welcome, Colin and Gabby, and thanks for coming, Balio. This is the week 9 webinar, so we're getting towards the end, and but it's not over yet. We still have a bunch more to do in the next few weeks, but I always like to give you a heads up on what's coming up. So let me share my desktop and talk about the plan today. So the plan today is I'll start out as always with any questions you might have, because it's always a big point is make sure you ask questions when you have them, and especially when there aren't that many of you here, because you're not bothering anyone else really, or not very many. Then you'll notice all the rest of the things we're doing today have something in common. What do they have in common? Yeah, chi-square. Okay, so this is really all about the chi-square distribution and what you can do with it. So I'll start out a little bit with the chi-square distribution, and then we'll use it, and we're going to use it to conduct some hypothesis test. Yep, it's a CHI is the way you do it in English, and it's chi. It's not xi. So by the way, I don't know if you know, but they skipped this letter for the vaccination, for the COVID variants. Nothing to do with the fact that it's used a lot in math, because they don't care about that at all. So do you know what else that letter could sometimes stand for? Why they skipped it? It's the name of the president of China. So they didn't want to name a COVID variant after that guy. But our chi-squared came way before he did, since this is a Greek letter. And we're going to look at the chi-squared goodness of fit test. And then after looking at the chi-squared goodness of fit test, we're going to look at the chi-squared test for independence. And then we're going to look at the chi-squared test for homogeneity. And those are going to be the 3 kinds of hypothesis tests we're going to be doing today. So just one thing is we're only doing hypothesis tests, no confidence intervals. That doesn't happen with this stuff. This chapter is hypothesis tests only. And it's an important one, and it's what we haven't done yet. So we have done, hopefully, when you're trying to figure out, what calculator to use on your, when you have a problem to work on, then you always ask, what kind of survey question is it? And if you remember in chapter 8, 9, and 10, the 2 types had either a yes, no answer, or you can make it a yes, no answer, or it had a numerical answer. What else is there? Yeah, categorical non-yes, no. And those do happen. Okay, things like, what state were you born in? Nobody would say, I was born in 6, or they wouldn't say yes. They would say, I was born in California. Okay, or what is your race? Okay, again, that's not a number answer. It's not a yes, no. What's your favorite color? That could be one. And that's definitely, not a number unless you're like me and you're a physics nerd, but otherwise it's not a number. But most of the things we're doing today are going to be things that are categorical, not yes, no. And it turns out there is a way of analyzing them, and we're going to be doing what's called the chi-squared distribution. But before I get into the details, let me ask you any questions about anything that could be your projects. It could be about, what's coming up in the next couple of weeks. Could be something else.
I've got a question about feedback on my discussion last week and questions about project 2. Should I save those for the end?
If it's related to others, like if other people would gain some knowledge because of it, then this is a good time. If it's kind of personal, you might want to save it till the end when it's not recorded. So it depends on what you're asking.
Okay, just a clarifying question then, and
Sure.
I'll have more questions later, but if we do matched pairs
Mhm.
for project 2,
Mhm.
we need 31 pairs or more.
Yes.
Okay,
Yes.
not 10 or 15. Some of the problems at various points I've only had a few, but
Right. But that's mostly because there's many problems,
yeah,
and
yeah.
if you're always asked to type in more than 30 pairs, that's a lot of busy work.
Yeah.
But this is a single project that's a big part of the grade. So I don't feel guilty making you type in, 31 pairs
Okay.
for one project. But I would feel guilty if it was, 8 different problems on a homework assignment. You know what I mean?
Okay. And then I guess looking at like things related to climate change, like temperature or precipitation,
Mhm.
if you do like the same place and the same time of year, but like, and then far apart, like in 2000 and 2020,
Mhm.
that would be a matched pair. But if you looked at like what would be independent instead of dependent? Like if you looked at weather in California, a random selection of cities. But I don't know. I'm just wondering if there's a way to do it independent instead of dependent.
Um, if you looked at maybe this year, Europe versus North America.
Oh, okay, yeah. Like where
And you
is
look
it?
at, say, 30, 40, 31 cities in Europe and 31 cities in North America to see if there's a difference in, I don't know,
Rainfall.
rainfall. Yeah.
Sure, okay.
And that would definitely, and not over many days, but over a certain day or something like that, or the total year's rainfall for
Yeah.
31 cities in each.
Okay.
And that would definitely be not matched pairs because, New York has nothing to do with London. You know what I mean? They're not paired up.
Yeah. I guess that's what I was just trying to make sure I understood the difference between dependent and independent.
Right. But if you're picking the same day with two different cities for many days, that would be matched.
Okay.
That would be dependent. Does it make sense?
Yeah, because like the day is the same, so it's the same
Right.
time of year. Okay.
Yeah, it's two outcomes coming out of one thought, and the thought is the day.
Okay.
Does that make sense?
Okay. Yeah. The day is in like January 15th.
Yeah.
Okay.
Yeah. So that, like I said, it's definitely and by the way, you're allowed to do match pairs, dependent data, and you're allowed to do independent data. But you're required to know which one you're doing.
Right.
Yeah. So if you're doing independent data, you better use the independent, calculator with, and again, you're not using the calculator that you've been using for the homework, you're using the spreadsheet. And that way it guarantees a transfer. That's why I make you do that. Yeah. And I've never had a student not be able to transfer it to general education statistics. And that's one of the big reasons is I make sure that it has all the things that the universities are looking for. And sometimes they're some universities are looking for spreadsheet. Okay, other questions? That was a good one because that is something that other people can learn from. Okay, if there's no questions, then let's talk about the chi-square distribution. So the first thing is, this is the way you write it. It's not an X, by the way. It's kind of a curvy, tall X, but it's not. And it's a Greek letter. The Greeks got to it way before we got to it. And the letter is called chi, C-H-I. And but of course the letter is that letter. So if you're any of you speak Greek? Yeah, I've never had anyone in my class ever speak Greek. I always ask it, and I've never gotten a yes. One of these days, but I've been teaching for like decades. Yeah, it's all Greek. Yeah, so it is a Greek letter. The square, that actually comes from the mathematics that I'm not allowed to talk about because it involves calculus. But what I will tell you about it, the one thing that you should understand is that if you square a number, then what can't it be? Give me an example of a number that it can't be. Yeah, it can't be negative. So the chi-squared is always positive or 0. It can never be negative. And because of that, we don't have two-tailed tests. We're only going to be able to have one-tailed test because there is no left-hand side if there's no negative values. Any questions on that idea? So this is definitely going to be one-tailed, and you're not, and it's only going to be right-tailed. There's no left-tailed. So that makes it easier. That's the good news. So you don't have to worry about, is it less than, is it greater than, is it not equal to? None of that stuff ever applies when we're going to be doing the chi-squared tests. Any questions on that? Okay, it might be worth it just to show you what it looks like. Probably should have popped this in to start, but I didn't. But it's always good to go to the book. Takes a moment, but I'll get there in a second. Sorry about that. Okay, so now we can see some pictures. So here's the chi-squared distribution. There's something called degrees of freedom, and that has to do with kind of how many different categories there are, it turns out, and it has something to do with them. I'm not going to get the details, but it looks different depending on this degrees of freedom. I actually created a app so you can change the degrees of freedom and watch how chi-squared changes. So again, if it's 2, it looks kind of weird. All the rest don't. All the rest go up and then down. And then if you look at it with a much higher degrees of freedom, then what's it starting to look kind of like? Yeah, now it's looking a little closer to normal. Okay, so it turns out that if you go really high, it's starting to look more and more and more normal. Okay, one thing though, there is no negative values ever for the chi-squared. Okay. Can you use it with 2? Yeah. But you tend not to need to. Typically 3, but you could, I guess you could do 2. 2 can happen. 2 is when it turns out you're comparing 3 things. So 2 will happen. Because it turns out the number of things you're comparing, you subtract 1, and that's degrees of freedom for a lot of these things, for some of what we're doing. So 2 degrees of freedom definitely happens. 1 is pretty rare to bother, but that's 1. Okay, so that's the distribution. And as I mentioned, we only deal with right-tailed tests. So, so if the chi-squared test statistic is 10, then the p-value is the area to the right of that value 10. And you can see it'd be pretty small if the degrees of freedom is 5. Okay, if the p-value is 18, it's really small because there's very little past 18 and below the curve. Any questions on kind of seeing the chi-squared distribution and what it looks like? Okay, now that we've seen it, it is time to, what is this a distribution of? It's the distribution of chi-squared. It's a math formula, but I'll show you what it's used for. That's more important, is what it's used for. The math I can't do in class, but there's stuff. That's all I can tell you. Okay, so that's chi-squared. And really, we're going to be looking at examples. So here's an example of something you might be interested in. And what it says is, in California, 39% of residents are Latino, 36% are white, 15% are Asian or Pacific Islander, 10% are other races. Okay. And I got this on Google. I think I got it last year though, but it hasn't changed that much. Is the distribution of races different for California community college students? So that might be something that you look at because, in a good world, we want to represent the population in California amongst our students. That would be a good thing to do. We don't want to discriminate against one or another. So a survey was done. Okay. And by the way, if I say a survey was done, I made this up, just let you know that, of 300 California community college students, and 125 were Latino, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. What can be concluded at the 5% level of significance? Okay, any questions on the question before I get into it in depth? Any questions on the question? Okay, so if there's no questions, I have a question for you. What's the survey question here? Yeah. What race are you, or what is your race? Okay. We're gonna assume they asked, like in classes, so you don't have to ask, are you a student? Like, I don't have to ask you guys if you're students because I know you are because you're my students. So, but what is your race is a survey question. And what is the kind of answers you're gonna see? Yeah, you're gonna see things like Caucasian, or white, I guess, or maybe Latino. So you're going to see, no one's going to say yes. No one's going to say no. No one's going to say 22. Okay. It's just a bunch of words that could come out from different categories. So this is a qualitative, not yes or no survey question. Any questions on that idea first? Okay, it's a qualitative, not yes or no survey question, which puts it in a category or an idea that we have not done yet. We've defined what it is, but we have not done a hypothesis test for anything that is qualitative, non-yes, no. So that's where the chi-squared is going to come in, is when you're dealing with that type of question, we're going to have a chi-squared test. So hopefully you know what's the first step in these kind of problems in a hypothesis test. Yep, we got to state the hypotheses. So we need to state what is the null hypothesis and what is the alternative hypothesis. And then what I'm about to do is really dangerous. And I'll tell you why it's dangerous. Because all of a sudden you're going to want to do every problem just like this, even though it's not it's not a chapter 9 or, it might be chapter 9 or chapter 10. So I want to give you a big warning is that chapter 11, the hypotheses look very different than chapters 9 and 10. And don't make the chapter 9 and 10 hypotheses look like the chapter 11 one. Got it? So now that I told you that, now I can tell you what the hypotheses are. And what makes them very different from chapters 9 and 10 is they're all words. Okay, no symbols. Okay, but in chapter 9 and 10, if it's a hypothesis coming from chapter 9 or 10, it must be all symbols or I take off points. Got it? So H naught colon, that stays the same. And then the racial distribution for California community college students is the same as what it is in California, just for general Californians. Okay, H1 is the racial distribution for California community college students is not the same as what it is in California. Okay, notice there's something in red. Maybe you're colorblind and you have no idea. What do you see? Distribution. With this kind of hypothesis test, if you don't put that word in, any guess what's going to happen to you on the exam and on your discussion post? Not fail, not quite fail. I'm not that mean, but you're going to lose a point. Okay, I will take off a point if you don't use the word distribution with this kind of hypothesis test. What we have here, and I want to emphasize this because we're going to have again 3 different kinds of chi-squared, and this kind we know the distribution of California, and we don't know the distribution of California community college students. We only have a sample for the students, but we know the full distribution for the state. And when you are conducting a hypothesis test to see if a distribution is different than another one, when you know one and you don't know the other, then we're going to use what's called the chi-squared goodness of fit test. And that's the name of the test. So we're going to use the chi-squared goodness of fit test. Okay, one of the hardest parts about this chapter is to decide which test to use. The rest is actually much easier than the last chapter. But we have tests that look similar. You got this big long paragraph, and you have to decide what type of test is the appropriate test to use in order to have good results, trustworthy results. Any questions at all on this idea? Okay, so there's a step-by-step process in doing the chi-squared test. And some of it you're already used to, like step 1 is to write down the null and alternative hypothesis. Step 2 is to decide what test to use. This time chi-squared goodness of fit test. And once you've decided that it's a chi-squared goodness of fit test, comes the next step. And the next step is something we haven't done yet. Okay, so the next step, just a second. The next step is to create a table and write out what's called the observed and the expected table. So let me show you the table. That's a really good question. Do you use the word distribution for all chi-squared tests? The answer is no. Goodness of fit test, yes. Okay, the next test, no. And the one after that is kind of. I can't, I'll get into more details a little later. Okay, so after deciding that we need a chi-squared goodness of fit test, you write down the test statistic, you write down the observed and expected table. So I tend to use the first letter. I tend to use O for observed and E for expected. Does that make sense? So that I usually put as the rows. And then for the columns, I write down the categories that people can answer the question into. Okay, and by the way, you could go the other way too. It's really, I do whatever fits on the page well. That's the important thing. Okay, but the important thing is you know that there's the observed and the expected. That's always going to happen when we're talking about a chi-squared goodness of fit test. And then there's going to be the categories for the other set. Then we go and see what are the observed. The observed are usually just given. In this case, we're told that 125 students were Latinos, so I put in 125 under the observed Latinos. I know that 92 were white, so 92 for white. I know that 33 were Asian or Pacific Islander, so Asian PI is the observed, is 33. And then finally, I know 50 were of other races. So I put 50 for the other. Any questions on that? Okay, next, we have the expected. That one takes a little bit of work. The observed, actually, I just wrote down. I just looked at the numbers that were given and I just put them in. Okay, the expected takes a little work, not hard work, but you have to know what to do. So the idea here is that a survey was done of 300 California community college students. Well, we know that in California, 39% of all California residents are Latino. So if the California community college population was the same as California, because that's what we're testing in terms of the distribution, then 39% of what we surveyed would be expected to be Latino. Any questions on that idea? So you take 0.39 times 300. And if I take 0.39 times 300, I get 117. So let me stop. Are there any questions on how I came up with that 117? Any questions on that? Okay, again, I always, like you to have questions if you do have questions, so please ask. Okay, all right. Similarly, if I want to find out what the expected for whites are, well, 36% of the California people or residents are white, and 36% of 300, that's 0.36 times 300. And you can pop that into calculator if you want, and you get 108. Okay, just a note, typically if you get a decimal, you typically round to the nearest whole number. It's typically how you do it. 15% of California are Asian or Pacific Islander. So 15% of 300 is 45. And then 10% are other races, and 10% of 300 is 30. Any questions? Any questions on how I came up, how I arrived at this table? It's the observed and the expected table. Okay, now if we look at the observed and expected, did we observe exactly what we expected? That should be obvious. Definitely not a trick question. Yeah, we did not exactly observe what we expected. Okay, right? We expected 117 Latinos. We observed 125 Latinos. So, well, if we observed a different number than we expected, can we say that the distribution of California community college students is not the same? Because, hey, we got something different. What do you think? Okay, so here's the problem. Here's the problem. Problem is we only looked at 300 students. And hopefully by now, you know that when you only have a sample, which is very small compared to the population of California community college students, there's something like 2 million California community college students. So we're not even like in the ballpark of the population. Then there's usually going to be some variation from what's expected. The bigger question is that variation higher than you would get under kind of normal circumstances? Or is that variation something that you would see if you just looked at 300? Any questions on that? Okay, now what I can't get into because it's very intense is the sampling distribution, standard error and stuff like that. I can't get into, well, how do you know whether that variation is high or low just by looking at those numbers? We used to do that, but we don't anymore because I can only do so much math now. But there's some math formulas that will talk about how extreme the variation is for any particular value. Okay, but what we can do is we can basically go to a computer and we can ask the computer to tell us whether that variation is a typical variation you would get with a sample size of 300, or is that so far from what you would normally get that we're going to say that things really are different. And that's what hypothesis tests are all about, right? Okay. And any guess on what distribution the variation from the expected or the observed and expected variations, what distribution you're going to end up with? Yeah, chi-squared. Okay, that was the whole point of me talking about chi-squared before. So if you actually look at all possible variations, then they're going to follow a chi-squared distribution. Okay, and it turns out we have 3 degrees of freedom because we have 4 categories, -1 is 3. Okay, any questions on that? So what I need to do is I need to go to the calculator. And we're towards the end of the class, which means you should look towards the bottom and tell me what number you think we're going to use. Yep, 21, goodness of fit, because we've identified this as a goodness of fit test because we have one population we know, we have a sample from a population that we don't know, and we want to see if that sample is like too far away from what you would expect. Okay. So is the distribution of the population that you don't know far from what you do know? So I'm going to click goodness of fit test. And it says type in the values of the observed and expected separated by commas. So I can go in here and I can, the easiest thing to do is copy the first row, paste it, and I need to put commas in. And then I can do the same thing with the second row. Copy it, paste, put some commas in. Notice it does not ask for confidence level. How come? That's what we're used to in these kind of things. Can you remember? All right, not seeing, I'll jump in. Remember, I told you in this chapter, we don't do confidence intervals. So there's no confidence level. That's not happening. So, but I can hit calculate. That's all I have to do. And I get a chi-squared, that's the test statistic, is 19.45 or so. And the p-value is small, 0.0002. So let's write that down. The test statistic was 19.45. Okay, and if you want, we can pop in chi-squared. There we go. Make it look prettier. And the p-value was equal to 0.00, was it 2 or 3 zeros? 3 zeros, and then a 2. So let me stop for a moment. Are there any questions on how I arrived at the test statistic and the p-value. Any questions? Okay, so now, so there is no confidence level. There's no confidence interval for the population mean or proportion. Yeah, we're not even talking about confidence intervals with chi-squared. You just can't even do it. Yeah, there is a significance level. What's the standard level of significance, by the way? Yeah, 5%. Okay, so when we have a p-value like 0.00022, you don't have to worry about it. That's lower than any kind of p-value you're going to see. Okay, in the real world, by the way, people usually don't give you a level of significance. You look at your p-value and you decide whether you have strong evidence, you have just regular statistical significant evidence, or weak evidence or no evidence. Okay, and that's what people usually do. But 0.05 is like that boundary for having evidence. Okay, so the conclusion. So in this case, I'm going to say strong because my p-value is really small. So there is strong statistically significant evidence to conclude. And one thing that you can do is you can literally copy H1, and after the word that, you just paste it in, maybe get rid of the red. And you just rewrite it, and maybe the should be lowercase. That the racial distribution for California community college students is not the same as what it is in California, period. Any questions at all on this example of a chi-squared goodness of fit test? Any questions? Do you agree that this looks easier than what we've been doing? I usually don't have you interpret the level of significance for these because it's a little hard to talk about because we're not talking about a difference of means or a difference of proportions. So it's a little bit hard to do that, but we should know that the p-value is small. Yeah, so I don't ask you to interpret the p-value because it's a little complicated. Okay, but I do ask you to do what I just did. Write down the table and then write down the test statistic and the p-value. Actually, before that, write down the null and alternative hypotheses. Write down the test you're using, the name of the test. Write down the table, the observed expected table. Find the test statistic and p-value and state the conclusion. So those are the things I'll be asking for these. Again, it's a bit easier. It's a lot easier than what we've been doing. But doesn't mean you have an easy week, because what should you be focusing on this week? That's not so easy. Yeah, the project. So that's a big deal, and that you definitely want to put a lot of energy into. So this week is kind of easy when it comes to the chapter, but you do have the project that you should be really focusing on. Okay, here comes the next question. Yeah, so hypotheses, pick the test, table observed expected, run the test statistic, p-value, state the conclusion. Yep, that's all you have to do. All right, so here's a different question. Does it matter what season a person was born when it comes to the type of car they drive? Table below shows the season and car type. And you see spring, summer, winter, and fall. Sedan, SUV, and other kind of car. Okay, because there's those that are the astrology people that think that, you know, it really matters when you were born in terms of your month or your season, because that changes your entire personality and all that kind of stuff. So your whole self is different. And the question is, do we have evidence for that? Any questions on the question? How is this different from what we just did? How is this different from the last example? Because it's very different. Okay, there's 3 samples. Instead of one populated, there's 3 categories. It's not quite it. It has to do with a survey question. What's the survey question? Yeah. So it's asking yes or no question. The yes, no question is pretty, that's a hypothesis test. And the hypothesis test is always at the end, yes or no, but yeah, it's the survey question. It's not a single question. We have 2 qualitative survey questions, where the first question is, what season were you born in? And for example, I would say summer. I'm a July baby. Okay. And what kind of car they drive? Okay. Any guess what I would say? I have a feeling you could never, ever guess the kind of car I drive right now. Okay. The answer is other. I don't have a car. I actually don't own a car right now. I'm doing an experiment. So that's why you wouldn't guess, because everyone owns a car. It's not a money thing. I'm just doing an experiment. So I'm another. So the point is, it's 2 different survey questions with 2 different qualitative answers. And we want to see whether knowing one helps you understand the knowledge of the other. Does that make sense? We had a word for that, where if it doesn't help you, it's called something, but if it does help you, it's called something else. What were those words? We had it in chapter 3. Don't you hate when I throw something way back? Yeah, independent and dependent. So another way of stating this is the following. So now let's write down, picking the test. Actually, let's go this way. We're going to use what's called a chi-squared test for independence. And that tests whether 2 different things are independent of each other or dependent. Okay, so you can have 2 survey questions. They're both qualitative, and we want to see if they're independent or dependent. All right, so that gives us an H0 and an H1. So H0 is the season a person was born in, and the type of car they drive are independent. Notice I highlighted independent in red, because that word has to be there when you're doing this test for your H0. Okay, and H1 is exactly the same as H0, except the last word. And the last word is dependent. So the season a person was born in and the type of car they drive are dependent. So any questions at all on this idea? All right. Now, hopefully you remember in chapter 3, we were able to say things like, is driving a sedan and being born in the winter, are those independent? Do you remember doing that? You may not have liked it, but we did that. And we looked to see if the probability of A and B was the probability of A times the probability of B. Okay. But when you have a sample instead of the full population, then those numbers are not going to be exactly the same. If we take that ratio, right, the 76 over the whole total, that'd be the A and B. And then we look at A, which would be the sum of the first row divided by the total. And then B, which would be the sum of the winter column divided by the total winters. Divided by the total, I mean. And you multiply those out, you're not going to get the same number because we got a sample. And you almost never get the same number if it's just some kind of sample. But the question is, how far off are you from the expected number you would get if they were independent? Any questions on that idea? And when you want to decide whether you're far off or not from what you would expect, then the chi-squared distribution is what does it for you. Okay, and the reason is way beyond this class. But what I do ask you is you trust me. Sound good? So, you know, I have done the proof and all that kind of stuff, you know, for classes in graduate school that I had to do. So you just trust me. If you don't want to trust me, trust the book. That's another author. And they come up with the same thing. You don't like their book, pick another book. They all have the same thing. So this works. Any questions at all on this example? Okay, so the next thing we got to do is go back to the calculator. Go back to the calculator menu because this is not a goodness of fit. What calculator number am I going to use this time? I tried to make it really obvious in terms of the titles. Yeah, this is 22. Test for independence. Okay. I don't know why I should have done it last week. This is this week. If you did it last week, you made a mistake because we didn't have this. Oh, 22, as in all the twos. Yep. Yeah. Tuesday, TWO's day. Okay. So now what we have to do, is kind of a pain, is we got to fill in the table. And copy and paste doesn't work so well with this table, but we can still do it. 73, 81, 76, 73, 81. So 73, 81. And then next is 76, 78. And then the second, 65, 68, 62. And then 64, then 43, 51. And then 48.50. Okay, any questions so far? By the way, it turns out that you have to make sure that the expected counts are all greater than 5. Now, with this example, it clearly is, because our numbers are all like, everything is bigger than 40. Expected is going to be bigger than, much bigger than 5. So there's no issue there. But just to let you know that that's kind of how you know you have a big enough sample size. And if you don't have big enough sample size, you can't do anything. You need to give up. So you calculate. And notice we get chi-squared. Okay. And we get our p-value. Do all the observed counts have to be greater than 5 in the chi-squared test? Or just in all. And it's technically all the expected counts. All the expected counts. So the expected counts all have to be greater than 5. Okay. And not 58. Not sure what you're asking. Huh?
You put 58 instead of 50.
Oh, did I type in the wrong number?
Yeah.
Okay, yep, that'll happen. Yep, that should be a 50. Sorry about that. Thanks for catching my mistake. 50. Okay. By the way, nobody's perfect. If I were doing this and my life depended on it, then I check it again. I give it to someone else to check, give it to someone else to check, and made sure that it was right. But fortunately, this is just a class experiment. Okay, so the p-value is even smaller. I mean, even bigger. So our chi-squared is 0.48. Okay, and our p-value is 0.998. So let's write that down. So chi-squared is equal to 0.48, and p was equal to 0.998. All right. Any questions so far? Okay, now hopefully all of you can tell me when you have a p-value of 0.998, what does that mean? Yeah, it's not significant. No one would ever say that's significant. That's about as big a p-value as you ever see. So that means we fail to reject. So when you fail to reject, hopefully you're used to the way you word things. You always start with there is insufficient evidence. And if you want statistically insignificant evidence, it means the same thing. To make a conclusion that, and then again, you can just take H1 and pop it in. So the good thing is, once you have written down what your H1 is, it's very easy. It's very easy to state your conclusion. You look at the p-value, and if the p-value is large, you say there's insufficient evidence, just like we've been doing for weeks. If the p-value is small, you say there's statistically significant evidence. To make a conclusion that, and then you just type in or paste in your H1. So I want to stop for a moment and make sure that there's no questions. Are there any questions at all about this particular example and a test for independence? Okay, and again, it's much easier to watch me do it than to do it yourself, because I'm telling you that it's a test for independence. When you have to do it yourself, you're just going to be given the question and you have to decide what test to use. And you have to know it's a test for independence and not for something chapter 8 or not a good as a fit test or something like that. Any questions on this? Any questions? Okay, now I have a third question to look at, or third example. And this is the following. And the question is, do single men and women take the same kind of vacation? Okay, be a nice little question to ask, right? Okay, and I want to give you a reminder. These are examples that I just made up. So, don't go tell all your friends that, hey, I learned that, men and women take different kinds of vacation or something like that. But hopefully, you know how to decide if you want to do that as your research project someday, not for this class, because project 2 is about chapter 10, not chapter 11. But maybe someday you're going to do some kind of research project. Okay. And the question is, do single men and women take the same kind of vacation? Table below shows the results of the study. So we have male, we have female. And the type of vacation we're looking at are international, out of state, but in the United States, and more local. So that would be, I don't know, traveling to Los Angeles or something. Okay. And we have numbers. Is this a goodness of fit test? Yes, not a goodness of fit test because we don't know any specific distribution that we're comparing to. Is this a test for independence? Okay, good guess, but not quite. Okay, it's a bit subtle that it isn't because we're looking to see if men and women have a different distribution of type of vacation they take. Okay, does that make sense? We're not seeing if gender is independent of type of vacation. We're comparing the two distributions for genders. Okay, it's very subtle. Okay, any questions on this idea? Okay, so once we have that, once you've decided that it's different, then we can write down our hypotheses. So our H naught is the distributions of travel types are the same for men and women. And H1 is the distributions of travel types are not the same for men and women. Notice this is similar to goodness of fit in the wording, but what's the difference in the key word? Yeah, plural. Okay, we're not comparing two unknown distributions, and in this one, we're comparing two unknown distributions. When you're doing goodness of fit, you're just looking at a single distribution and comparing it with a known distribution. So it's slightly different. It turns out the math is very different, but the math for this test and the test for independence are the same, it turns out. So it's kind of weird. So that's, just trust me on that one. And the name of the test, it's called the chi-squared test for homogeneity. Okay. And do you know what homogeneity means? As an English word, not as a math word? Or homogeneous, you might have heard it. Yeah, it's kind of the same, means have the same patterns. Okay, same stuff. So that's why we call it a chi-squared test for homogeneity, because the distributions are the same or not the same. We're testing to see if they're the same or not. Okay, I want to give you some history that's kind of interesting. Is that as I mentioned, I've done a lot of consulting just for various people and groups and agencies and companies. And what I noticed is that this chi-squared test for homogeneity, I needed it all the time. Okay, for some reason, a good percentage of the consulting I had to do needed chi-squared test for homogeneity. And the book that we were using, the OpenStax book, and the one I used before didn't even have it, didn't cover it. So this was a long time ago. This was about 15 years ago. I emailed the author of the book. And I said, in the next edition, can you include the chi-squared test for homogeneity? Because that's like one of the most used tests that there is in terms of the real world. And you know what she told me? Can you guess? This was Barbara Lowski, who I knew. And she knew me also. Okay. She told me, that'd be great. Can you write it? So That was the one section on the author in. So I wrote it, but it didn't take that long. It was, I don't know, a few pages. And I wrote, so in the book, that's my writing. So I wrote that part of the book. And now everyone's using it. Okay, it's like one of the main books that people use in statistics. So, it's always good when actually, change something a little bit. So I was able to change something because that was so important in the real world that it should be taught in elementary stats, and I convinced everyone. So that was kind of neat. Okay, so it's called the chi-square test for homogeneity. It's really important whenever you're comparing two different groups and to see if the two groups have the same distribution of something that is a qualitative variable, then it's chi-square test for homogeneity. Any questions on that so far? Okay, so now what do you think we have to do? Hopefully you all know, because we've been doing this for a long time, this process. Once you've written H0 and H1 and decided what test, what's the next step? Yeah, you go to the calculator. So I can go back to the calculator menu. And hopefully you can tell me which one. Yep, 23. And by the way, notice how many left are there? Yeah, there's only 2 left. We're almost done with this class. Okay. As you might guess, next week, we're doing 24. And the week after, we're doing 25. And that's it. So we only have a little left. Okay. 24 is pretty deep. 25 is not. 25 is pretty easy. So we end kind of easy. Okay, so I'm going to go to test for homogeneity. And here, notice there's only an A and a B. Okay, there aren't 3 columns because that's the whole point. We only have 2. So I'm going to go ahead. I'm going to put in my 29, 47, 33 for my A. 29, 47, 33. And then I'm going to put in 38, 42, 36. So 38, 42, 36. Any questions on that? Then I scroll and hit calculate. What do you notice? Yeah, not very significant. P is very high, about 0.5. Chi-squared is about 1.4. So just to make life easier, copy, paste, and change. So our chi-squared, again, was 1.4. And our p-value is about 0.5. Okay, and notice it's 0.5, not 0.05. Big difference. So that's a giant p-value. And when there's a giant p-value, hopefully you know that you can say there is statistically insignificant evidence because the p-value is small to make the conclusion about whether or not the distributions of travel types are the same for men and women. Any questions on that? Just want to let you know whether or not you should only use when you fail to reject. If you reject, it's not a whether or not. Then you say there is significant evidence to conclude that. Any questions on that? Okay, so we've now seen 3 kinds of tests. Let's do one more example. Okay, so here's the example. A study was done asking people how far they traveled on President's Day weekend. Okay. The mean was found to be 120 miles, and the standard deviation was 40 miles. The table shows the results. So here we have some stuff, and I'll talk about the table in a little bit. In fact, let me do this. Let me not put those in yet. We'll get those in a bit. So we have less than 80, 80 to 160, and greater than 160. We had 56 that were less than 80, 61 that were between 80 and 160, and 12 that were greater than 160. And the question is the distribution normal? Okay, so earlier, the only way you had an idea of deciding whether the distribution of something was normal was to do a histogram and look at it. And just kind of say, yeah, it looks pretty bell curvy, right? That's not mathematical. Now we have a mathematical way of determining normality. Okay, and I want to let you know, if you really want to determine normality using a test, it's something similar to this, but it's more intense. And if it's more intense, what does that mean, given that we're in week 9 of the class already? How are you going to learn that? Yeah, you're going to take an upper division statistics class and not elementary statistics. And then you're going to learn, tests for normality that are much deeper. And this is just kind of the beginnings of it. There's an elementary piece of it. Okay. And there are definitely, tests for normality. But again, I'm kind of showing you the beginnings. Any questions on that? Okay. So now what we want to do is kind of think about what we've learned in the class to decide on how do you get the expected counts. So specifically this number 80 and this number 160, they're important numbers. How come? Okay, those aren't just some random numbers. They're necessary. This would be much harder if I used 90 instead of 80. Yeah, it's 1 standard deviation above and below the sample mean. Okay. So if we had a normal distribution, what percentage of the data should be within 1 standard deviation of the mean according to the empirical rule? It's been a while. Okay. Your memory is not perfect. It's not 64%. 95% is 2. Yeah, 68% is 1. So that was something that we had, that was part of the empirical rule, that if you have a normal distribution, 68% of the data should be within 1 standard deviation of the mean. Okay, any questions on that? All right, so if you look at the observed, then we had 56 and 61 is 117 and 12 is 129. So if I go ahead, pop in a calculator, 129 times 0.68, get about 88. I'm going to round in the nearest whole number. So I get 88 for my expected value, expected number between 80 and 160. Any questions on that? Okay, now notice again, we had 129. That was our sample size, right? So if there's 129, we expect 88 of them to be within 1 standard deviation. Then I subtract 88 to get how many outside of one standard deviation. And 129 minus 88 is 41. Okay, I did that in my head. You don't have to, though. You're always allowed to use a calculator. Okay, 41. If you take 41, that's how many are outside. But to the left, it should be half of that. And half of 41 is? Yeah, 20.5, you round, you get 21. And that'll be on both sides. Any questions? Any questions on that? So what's the next step? We have to decide what test we're using. Yeah, this is goodness of fit because we have one group that we don't know the distribution, and we're comparing it with the known distribution, which is normal. So because of that, we can know it's goodness of fit, and we can write down our null hypothesis and alternative hypothesis. The null hypothesis is it's goodness of fit, so it has to have the word distribution. So the distribution of travel distance during President's Day weekend is normal. And H1 is the distribution of travel distance during President's Day weekend is not normal. Any questions on that? So notice we've been doing something for weeks and weeks now, but we kind of stopped at a point. And that is, I'd ask you, do you need to make the assumption that you have a normal distribution? Remember that? I've asked you that many times. But now we actually have a way of testing to see if that assumption is completely invalid. Because if you end up with a p-value that is low, then you say, hey, it's not normal, don't even try. Do you see that? So that's one of the big reasons to decide to do this test. Because if you get a low p-value, then you cannot assume you have a normal distribution because it's just a stupid assumption. Do you see that? Whereas if you have a very high p-value, then the assumption is not unreasonable. So that's kind of the big purpose of this particular test that we're doing. This goodness of fit test for normality. All right, now you should know what to do next, which is go to our calculator. So let's go to the calculator. We need to go back to the calculator. And we're still at goodness of fit. We're back at goodness of fit. It's asked for the observed and the expected. The observed were 56, 61, and 12. And the expecteds were 21, 88, and 21. Any questions so far? We calculate. Okay. Is the p-value 4.44 about? Yeah, it's not 4.44. The kind of sad thing is I did something very similar to my face-to-face class this morning. 100% of the students made the mistake and wrote that down. Please do not make the mistake of not seeing this last bit that says E negative 16. So that E negative 16 means move the decimal over 16 places to the left. Okay, this p-value is incredibly minuscule. Any questions on that? Okay, and notice the chi-squared is gigantic, right? That's 70 point something. It's gigantic. So the p-value is really tiny. A lot of times people just say the p-value is less than 0.001. Sometimes you'll just see that because that's enough. If you're less than 0.001, you're always going to reject the null hypothesis. I don't think I've ever seen anyone use a smaller level of significance. Okay, and we're much less than that. Any questions on that? Okay, so then we can make our conclusion. And there is, I'm going to even emphasize it more, very strong, because that's a tiny, tiny p-value. Strong statistically significant evidence to conclude that the distribution of travel distance during President's Day weekend is not normal. Any questions? Any questions on this goodness of fit test? Okay, so we tested to see if it was normal or not. The other test that you'll see sometimes, which is goodness of fit test, instead of normal, what's another important distribution that we've been looking at in our class? We kind of had a whole chapter on it. Besides normal. Yeah, uniform. Okay, so often you'll be asked to see, is the distribution uniform, which would be the same thing as, are all the things the same? Okay, is this normality test used in the real world, or do they always use the more advanced normality test? In the real world, I think I've always seen the more advanced ones. But this is the beginning of the advanced. Kolmogorski's test for normality. Again, I'm not getting into it, but that's a test for normality, and that's the one I see a lot most of the time. There's a few, but that's the one I see most of the time. But that's an extension of what we're doing right now. Okay, whereas chi-squared is usually used for uniform. Okay, and uniform doesn't have to be continuous, because we had a chapter on continuous distributions be the uniform, but you could also have uniform for discrete. So that would be like if somebody's rolling a die and you think they're cheating, then you could do a chi-squared test to see if it's uniform, to see if the answer, the rolls are the same. Okay. Same thing with cards. So you want, if someone picks a card, then is the card uniformly distributed? Okay, and in particular, you want to say like 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. So are the cards that get picked uniformly distributed? Okay. Just to let you know, anyone know how I use this personally a long time ago? Yeah, in the casinos, in the old days, before the corporations ran them, the mafia ran them, so they'd bring in a cheater to cheat against me, and I would do a chi-squared test to see if the distribution was uniform, and if the chi-squared, if the p-value is really small. By the way, if the p-value is small, do you get mad at him and yell at him and say that stop cheating? Yeah, you run, you get the hell out of there. This was mafia, you yell at the mafia. And that's what I do, I just get out of there. I didn't need to run, I just walk out usually, but That's what I do. And then I come back and hopefully the next dealer won't be cheating on me. But that was real. Okay, did that. Now you don't have to worry about that because it's all corporate. Okay, so anyway, so I've used this stuff in a big way. So I want to let you know how important this stuff is, this chi-square distribution stuff. You'll see it a lot, which is why, by the way, this week's, I'm having you find the chi-squared online. That's done in a peer-reviewed journal, and they're everywhere. So secret word. Secret word is known. And that is because when you're doing a chi-squared test for goodness of fit, you're testing to see if the distribution of what you don't know is the same as the distribution that you do know, or the known distribution. So that is the secret word for the week. And that is pretty much everything I need to say for this week. I got about my goal on time. I always try and end around hour and 20 minutes or so, somewhere between hour and 20, hour and 40. And we don't have to talk too much about the project, but I'd be happy to answer any questions you have. I'm going to stop the share. And I'm going to stop the recording.